So yesterday, one of the important aspects what we were discussing about is the electrophilic addition reactions for alkynes. So generally what we see when you compare alkenes and alkynes are less reactive than alkenes towards electrophilic addition. There are primarily three reasons for it. One, if it gets added, it would have a carbocation, which is vinyl carbocation form. And vinyl carbocations generally are unstable as compared to that of simple 2-degree carbocations, which we get it from alkenes. Second reason being cyclic intermediate, like bromonium ion, which is formed during the electrophilic addition. In case if there is already existing double bond is there, so being a 3-membered ring with a double bond, it will become very, very highly strained ring. Okay, so these two are the prime reasons for not forming that Br plus that easily. Next, and high percentage of S character within the molecule. So if you see between these two carbons, the polarization becomes very difficult because of the high percentage S character. Okay. Next, we also took to the case that based on this, we can say one thing, that when it comes to bond dissociation energies, breaking carbon-carbon bond, double bond or triple bond, this is the usual energy that is required. But when you make a bond, okay, on a double bond, the amount of energy released as compared to that of a triple bond to convert into a double bond, here the energy release would be more, which tells us the second pi bond is more reactive than the first pi bond. So when it comes to hydrogenation, second pi bond will have more reactivity. Okay, so till this point we have discussed. Now getting into the next aspect about all the chemical reactions based on this, two fundamentals what we have learned. So let us see first the reactions which are addition of HX. Now if we check CH3C triple bond CH, when we treat that with HCl of one equivalent, then it will become CH3 CH double bond CH2 and Cl gets added here. If we add one more equivalent HCl of one more equivalent here, so that CH3 gets again added onto the same location here, and this will become CH3. So the product we'll get is gem dihalides. Let's seek the mechanism for the same. CH3 C triple bond CH is believed to extract the proton, relieving Cl minus, generating a less stable carbocation, which is vinyl carbocation. So what we are getting is vinyl carbocation. So the reaction is pretty slow because vinyl carbocation is not very stable. Then Cl minus in the solution will attacks on the vinyl carbocation to get vinyl chloride. Once you get vinyl chloride, H plus is being added to this. So we have two chances, one to get CH3 CH Cl with CH3 with positive charge here, or we can also get CH3 CH2 Cl. Okay, sorry, there is no H here. Yeah, so CH2 with CH2 positive. Okay, now most of the cases here, this is also withdrawing, this is withdrawing in nature, this is also withdrawing in nature, but the plus R effect of chlorine will make it more stable. Although overall it is withdrawing, and here also it is overall withdrawing, but if you see the ability of withdrawing nature, the second one would relatively be more stable. So here you will have more stable carbocation. So hence, if we check out CH3C Cl plus CH3, this will be treated with Cl minus. Cl minus attacks here, we'll get CH3 C Cl and CH3 as the major product. Make a note, everyone. lesser effect of Cl minus is more effective for overall stability of carbocation. The easy way to remember, whenever you add 2 moles of HX, there's a mechanistic way. What is the shortcut is whenever you add 2 moles of HX, both halides add it always on the same place at more stable case. So which means given any triple bond, if triple bond is given here and you have to add that with 2 moles of HX, make sure that you add both halides here only and both hydrogens at the terminal carbon. So that will be the major product, right? Next example, suppose if you have CH3, C triple bond, C, CH2, CH3. One side there is methyl, one side there is ethyl. First I'm adding HBr of one equivalent. See what are the products we can expect. We can see CH3, CHBr, not H, Br with double bond CH2, double bond CH and CH2, CH3. This is one product. The other product you can get is CH3, CH double bond C, Br with CH2, CH3. It's very difficult to specify which is a major product in here, because here this side there is a methyl group which will try to stabilize this double bond by inductive effect, and from here it is inductive and hyperconjugation. Here also the same case, here methyl is supporting, here ethyl is supporting. So the tendency to come both of these products is same, correct? So we can't exactly judge what is the percentages which you will get. Okay. On top of that, it would come across E or Z product also. There is no specific way of attacking here. So we can get trans and cis also. Here also we can get cis or trans also. So if you were asked the number of products, you should write all 4 of them. So with respect to this, the total number of products when one equivalent of HBr added, how many possible products you can get is 4 of them. Okay. Now if it was given 2 equivalents, HBr with 2 equivalents are given, then on the same case you will be adding Br, CH2, C, Br, Br and CH2, CH3. So overall what we can say, overall we check out regio wise, it is definitely following Markovnikov's addition. Markov addition is followed. Next stereo wise, it is not specific at all. So it is non-stereo specific. Non-stereo specific.
Sir, why it is Markovnikov addition?
When it comes to CH, here in this case, where we have a triple bond, suppose in case if you check out here, there was a H here, correct? So halide is not adding onto this carbon, it is adding onto this carbon, right? Okay, so which means it is following Markovnikov's addition.
Okay, sir. Sir, here in 2 equivalent case also 50%, 50%.
Beta, we can't judge exactly how much percentage you can get. Okay, the possibility of getting both the products is highly probable.
Okay.
Next, see in case if we have peroxide, the same concept of anti-Markovnikov will be followed. So HBr shows anti-Markovnikov addition in presence of peroxide. So in case if you have CH3, C triple bond CH, and we add HBr in the presence of any peroxide like R2O2, we will get CH3C H double bond CH Br. We'll get this as CHBr. One more mole if you add like HBr and R2O2, even The second time also you will get anti-Markovnikov's addition with 2 BRs coming at the position here. So always, if you realize, gem products are the ones which are more familiar. You'll always see gem products here. Right. So this is the first reaction where we are reacting with HX. Second is addition of X2. Addition of X2. Here, regioselectivity wise, it is non-regioselective. Okay. Non-regio. But when it comes to stereo, it will be anti-stereo specific. Anti-stereo. For example, if you take CH3, C triple bond CH, treating with Br2 and CCl4. So first we will get CH3, then we will have Br being added here, C double bond C, Br gets added here, and H. This will be the major product because this is a trans product. It has come from the anti-addition. While the minor product would be CH3, Br double bond, right? C double bond C with H and Br. This will be the minor product, which is coming by syn addition. Clear on that? Mechanism is the same here. CH3, C triple bond CH, as you treat with Br2, pi bond attacks here, removing Br minus. The attack is pretty slow because it is not going to give a very stable product here. So you will have this double bond CH with Br getting connected. Then the next Br that comes here, it doesn't matter whether it attacks from here or here. So it is non-regioselective because both of them will give same product only. So hence we will get CH3, C, Br with CH2, double bond and Br here. So that's how the addition happens, and the final products will be usually trans as major. If you give 2 moles, it will further react. Okay, let me mention that also. Br2 in CCl4, we will get this as CH3, C, Br. There is no regiospecificity here, no beta. So we'll simply have Br moles here. Okay. Next is the addition of X2 in water. So X2 and H2O. Okay. Or we can also write this as HOX, where this can be viewed as H minus and XS delta plus. So the del X plus will act like the electrophile, OH minus will act like the nucleophile part. So we can definitely say regiospecificity exists here, which will go through Markovnikov's addition, and stereo, non-stereo here. Okay, non-stereo. Why non-stereo? Let us see. First, if you write the overall reaction, CH3, C triple bond CH on treatment with HOCl, we would first get as CH3, C. We will get this as OH double bond CH Cl. CH, then we have Cl here. Okay, this is how the addition happened. But whenever you have enol form, enols are highly unstable form, so they will immediately convert into keto form, and the final product will end up as CH3 double bond O CH2Cl. This will be the final product. Considering I take one equivalent of the reactant. So when I take one equivalent of the reactant, this is what would happen. Okay. Suppose if the same reaction, if I took 2 equivalents, C triple bond CH and HOCl of 2 equivalents. So first, this would form COH double bond CHCl. This will form. Again, the second mole will attack here to form CH3, C, OH and OH with CH, Cl and Cl. Okay. Same is the problem here also. Two OH groups on the carbon cannot exist for a long time, so they will come out as H2O, and again the keto group will form. So the only difference in the first reaction and second reaction is the number of chlorines. You see, First reaction will have only one chlorine here. Second reaction will have two chlorines here. That's why it is non-stereospecific, correct? Because eventually it will end up giving out a keto form. Make a note, everyone.
H2O is removed, sir.
Beta, H2O is removed here. OH and H is removed.
Why, sir?
See, any carbon containing two lone pair containing groups like OH and NH2, like OH and any halide, correct? So if carbon contains these two, because of the lone pair repulsions between these two, lone pair repulsions here, they would be unstable form. So instantly what would happen? The lone pair present on this oxygen will push the electrons towards carbon to ensure it is removing the other OH. So what would happen here, beta? So we'll get this as double bond OH plus OH minus. So the OH minus will take away this H plus and will end up forming C double bond O. Okay. So the other two bonds are like this. Clear? Same is the case here also. Now here whether the OH will push or N2 will push depends upon the solvent. If the solvent is ammonia, let's say solvent has NH2 minus in it. So NH2 minus is the one which is pushing. So the lone pair from here will push. This will come and you'll get this as C double bond OH, C double bond NH2 plus OH minus will take away this H plus and form C double bond O NH, imine formation. Clear, beta? So every time you have two OH groups or two OH and NH2 group or any lone pair containing two groups, they'll always be pushed to get a more stable double bond O or double bond N. No, sodium amide. Acha, in the second case here, yeah. In case if it is NaOH solution, then NH2 will be released. Okay. This type of mechanisms you will keep coming across as you go towards aldol and aldehydes, ketones. You will come across these reactions a lot. As of now, just remember it this way: two lone pair containing groups on the same carbon can't hold for long, so they will immediately remove out, and residue, and eventually you'll get a product here. Correct. Next, in case if we have CH triple bond CH reaction with HOCl excess. If I took excess, so what would happen? See, I'll go step by step here. So first step is CHCl double bond CHOH. But since it is excess, again the reaction would take place. So we'll form CHCl and Cl with CHOH and OH. Okay. Next, if you have Cl2CH C double bond OH, this is what is formed so far because H2O will come out of it. Okay. Next, from here, if you see, HOCl will act like a oxidizing agent for an aldehyde. In case if it is still at aldehyde position, it will act like an oxidizing agent and it will oxidize Cl2CH, this part as OH. So the final product will be ended up at acids in case if there is any aldehyde form remaining. Correct? Everybody understood that? So in case of aldehyde form is remaining, that will be further oxidized. So the important note is HOCl or HOX oxidizes aldehydes to acids. Right. See the next one, hydration reactions. So basically we are trying to add H2O here. Okay. So for H2O addition, the reagent that is used is usually HgSO4 in the presence of dilute H2SO4. It would be given this way, or it will be given as Hg2 plus in H plus, or it is mentioned as H2O, Hg2 plus and H2SO4. All of this meant the same thing. Okay. So here it is addition of H plus and OH minus. Eventually that is what is happening. This particular name of the reaction is called Kuchros reaction. And if you see in the past JEE questions, this has been one of the most commonly asked questions. So you must know how the hydration of alkynes work. So let us see first the examples, how to do it. First example, CH3, C triple bond CH in the presence of HgSO4 and H2SO4 and water If we take, we will get this as CH3, COH, double bond CH2. This on tautomerism will give CH3, double bond CH3. So this is the final product form. Okay. Second case, so if we check out CH3, C triple bond C PH in the presence of Hg2 plus H2SO4, we will get CH3, CH double bond C PH and OH, which sorry, on equilibrium will form CH3, CH2, C double bond O PH. Okay, this will be the major product. In short, if you check out, it is definitely following Markovnikov's addition. So Markovnikov addition is followed, that is a regioselectivity, and H2o addition without rearrangement. Can you see it is nothing but an oxymercuration demercuration? So it is same as oxymercuration demercuration, except the reagent is slightly different. There we used to use HgOAc twice. Here we are directly using HgSO4. Okay. Let's see the mechanism here. So this will take to the root of electrophilic addition mechanism. First, we will have CH3, C triple bond reacting with Hg2 plus ions present in the solution, right? And Hg2 plus will have high polarizing power, so it will start polarizing the triple bond here. So there is a slow reaction that will take place, and that will polarize the bond to get CH3, C double bond CH, and a mercury bridge is formed this way with 2 plus. Okay. This type of a bond formation is observed. Then H2O will attack from the opposite side and always attacks on the more substituted side. This we have learned in OMDM also. So as it attacks, this bond will break towards mercury. So we will get CH3, and I'll keep writing the equilibrium part because it is all driven on both sides. So H2O will attack here, bond will break. So we'll get CH3, C, OH2 plus with double bond CH and Hg plus. So this is what we have got so far. I guess the point is clear, everyone. Right. So from here, H plus is being removed. So we'll get CH3, C, OH, double bond CH, and Hg plus is remained. Okay. It can undergo tautomerism. So here it will undergo tautomerism. So we'll get this as CH3, C double bond O, CH2, Hg plus. This is what is left out with. Okay, so far. Okay, right. Now Hg plus, leave away the electrons here and come out as again Hg2 plus, on which we'll have CH3, C double bond O, CH2 minus formation, which on treatment with H2O will take this H plus to form CH3, C double bond O, CH3. Okay. So what we have added is we have added H plus and we have added OH minus. So addition is all about H plus and OH minus, but that OH will convert that into a keto. Hg2 plus is acting like catalyst only, beta. It polarized initially so that H plus and OH minus has been added, and then it will come out as again Hg2 plus. Correct? The reason being C double bond O is present, carbon's electron negativity is increased, so it will pull the electrons towards itself, reeling out Hg2 plus. And a very small catalytic amount of Hg2 plus is added, that is sufficient for reaction to happen. Okay. If it was happening in C, no, this is a much easier available reagent as compared to that of OMDM, which means if we take CH3, CH double bond CH2, okay, why didn't we use HgSO4 in the presence of dilute H2SO4 directly? The reason we didn't use this, instead of that, we went for OMDM, that is HgOAc twice in the presence of H2O. And then we did the demercuration part. Why we use this instead of this is, this is an acidic solution, beta. HgSO4 in dilute H2SO4, which means there is abundant amount of H plus present. So instead of this getting bridge formation with mercury, the pi bond will directly attack H plus and it would get a secondary carbocation here. So it becomes simply addition, and from once a classical carbocation is formed, it can go for rearrangement also. So to avoid that rearrangement, okay, this reaction is done specifically in HgOAc twice and H2O. While when it comes to triple bond, the positive charge which comes is highly unstable, no? Because it is vinylic carbocation. So hence this can be used in triple bonds, not for double bonds. So these type of questions usually come, like why HgSO4 is better reagent for triple bonds and not for double bonds. So in double bonds, it will undergo classical carbocation formation, which we wanted to actually avoid. And if that happens, rearrangement is evident. Rearrangement takes place. So if you want to avoid this, then you have to go for OMDM, oxymercuration and demercuration. Right. Let us see about the hydroboration oxidation here. Suppose if you have CH3, C triple bond CH, and I treat directly with, if we treat that with B2H6 THF, okay, and then in case if we add what is that, H2O2 and OH minus, which is oxidation step, correct. So this will take up to the end, even the enol form, whatever the enol that is forming, it will again further react with it, and it will make C double bond O and H. This is what you will get anyway. Okay. So B2H6 will definitely make this reaction, and on top of that, the aldehydes which are forming, right, there is a reaction of B2H6 with aldehydes also, and further reaction will take place to form this as alcohols. So CH2OH will be formed. Now I want to avoid this reaction. I want to end it at only at aldehydes. So we do not want this to get into the alcohol form, which means I need to do a very controlled amount of addition and oxidation. So this can be done when we use, secondary isoamyl boron. So SIA, right? When we use SiA2BH, secondary isoamyl boron. So basically the structure is this way, with group here and group here, group here and group here with H. So this is secondary isoamyl group. Or we can also use it as 9BBN. Okay, 9BBN. So the structure is this way. Both connected with boron and hydrogen. This way. So this is actually 9 bora bicyclo 3,3,1 nonane. That is the IUPAC name of 9BBN. So 9BBN and SiA2BH are better reagents to be used instead of directly using B2H6. All right. So what is the reaction that can be done here? So we can see CH3, C triple bond CH in the presence of SiA2BH or 9BBN. Any of that if you take, you'll get C double bond C, CH3, H here, and B boron gets connected here with SiA twice. Or if it is BBN, then it will be BBN here. That on further reaction with H2O2 and OH minus, so it would have the enol form. So you'll get this OH here, CH3, H and H. So the enol so formed will undergo tautomerism to give CH3, CH2, C double bond O, H. So we get this particular aldehyde. Okay. Everyone is aware of Bayer's reagent, cold dilute KMNO4, which is alkaline, right? So suppose if we have R, C, triple bond C, R dash, and I treat that with Bayer's reagent BR, I'm just writing it as BR. We can use that as RC, OH, OH, COH, OH, and R dash. And that would be unstable form. So it will remove water to give alpha diketones. So you'll get this as alpha diketones. Right. So in case if we have R, C, triple bond, CH, and if Bayes reagent is used, first we'll have R, C, OH, OH, and C, OH, OH, and H. This will be unstable to give keto form here, and this side it is aldehyde. See, aldehydes can be further oxidized by KMnO4. So again with Bayes reagent, it will get oxidized to become RC double bond O, C double bond O, OH. So this will become alpha oxo acids. So it will become alpha oxo acids. In case both side, if there is aldehyde, like we have CH triple bond CH, and I'm treating that with Bayes reagent. First, it will form formaldehyde. Glaxol. And again, since it is an aldehyde form, so Bayes reagent will further react to give oxalic acid, COOH. So in case of alkynes, we'll get oxalic acid when you treat with Bayes reagent. In case if you treat with MCPBA, RC triple bond C and R, and if I react that with MCPBA, what we expect is this: R, C, double bond C, R dash, and then oxygen will come. And that's how epoxidation is done. But observe this cyclic ring carefully. It has one pi bond here, one lone pair here, making an conjugation within the cycle. Sorry. What form is that? It is an anti-aromatic ring. So at any period of time, does it prefer to get this anti-aromatic form, students? No. Hence, especially when it comes to triple bond, we can clearly say that peroxy reactions won't happen. I can note everyone. Hot alkaline KMnO4 or acidic KMnO4. So if I take these two cases, we know that wherever there is a double bond forming, it will break that, right? So if you have RC double bond O, triple bond. First we have RC triple bond, R dash this way, and I treat that with KMnO4, alkaline, and heat. First you'll get the formation of ketones, double bond O, and R. Up to this point, it would similarly go as that of Bayes reagent. And once you get alpha diketones here, the bond breaking will start. So bond will break here. So bond will break to form acids RCOOH plus R dash COOH. But since it is in basic medium, eventually it will become salt RCO minus and R dash CO minus. If it was given in acidic medium, you will end up at acids only. So these are the two products you will get. Same way, if you have R, C double bond O, R, C triple bond C and H, and treat that with KMnO4, alkaline, and heat. So first I'll get R, C double bond O, H. Up to this point it is fine. Then the bond breaking will happen here. So after the bond breaking, you will see that it will form RCOO minus, considering it is in base. Single carbons will always convert into carbon dioxide. In case if you have both sides only one carbon here, and I treat that with KMnO4, heat and alkaline, then we will get this as HC double bond O, H, Glaxol. That will further oxidize. This all will undergo further oxidation to give 2 moles of carbon dioxide. No, that is an acid-base reaction. Whatever the acid which has formed, because it is in a basic medium, it will convert into a salt. Okay. This is an alkaline medium, beta. First it will form an acid, then acid-base reaction will take place. Clear?
Okay, sir. So will it occur in third case also, sir? After the formation of the...
Yes, here also.
Oxalic acid.
Same. When you write in terms of oxalic acid, here also we'll write it as CO minus. Ozonolysis reaction will go through reductive or oxidative ozonolysis. We have done that before. So see how the reaction need to be carried out. RC triple bond C, R dash is present here. First, if you treat with O3, and second, if you treat with DMS or zinc, right, it will undergo reductive ozonolysis. Through reductive ozonolysis, the product what you will get is a diketone. This is where it will end. See the mechanism. So first, the ozonoid formation, remember molozonoid formation. So C and R dash, oxygen, oxygen, double bond O with minus and plus. This is how it is, correct? So this will attack here. Pi will attack on this oxygen. This pi will shift onto this. So we'll get a molozonoid form, which is R, C, double bond C, R dash with O, oxygen, O, and this center oxygen. This is molozonoid form. And molozonoid form slowly will break into the formation of this double bond. Same mechanism, there is no change in the mechanism. Here also we will get this as R, C, double bond O with C here with O and O minus with R dash. This is how it is. And this gets positive charge. The only difference between that double bond and triple bond, here in double bond this bond will also break. In triple bond only one bond breaks here, right? So the rest of the mechanism is same. This will attack here, the lone pair present on this oxygen will attack here, and that would give us R, C, we have O, R, C with O and C with a bond here, R dash, O and H, okay? So when it was a double bond, it was only a hut. Now this is a hut with a balcony, right? So it would have a double bond. I mean, that bond will be existing here. So this is a kind of ozonoid which is formed in this case. Clear, guys? So once you get this ozonoid formation, right, bond will break here, this way. Bond will break here, bond will break this way. So we'll get this as R, C, double bond O, C, double bond O with R dash plus nascent oxygen. So if you are using any oxidizing reducing agents like zinc and DMS, that will control the nascent oxygen, and this is where the final product will be. You can see this is the reductive ozonolysis. So what is the difference here between reductive and oxidative? See RC triple bond C R dash, which is forming here. First it will react with O3, second it reacts with H2O to give RCOOH plus R dash COOH. It is happening similar to that of acidic KMNO4. So if you take acidic KMNO4, you'll get acids, right? All three bonds will be broken and it will become acids. Think in the same lines. Mechanistically, if you check out how it is happening, first an ozonoid is formed. How does it form now? R, C, triple bond, R dash. Okay. And we have seen that O, oxygen, double bond O with minus and plus. This attacking here, the pi bond shifting here. So we will get a molozonoid form, R, C, double bond C, R dash with O, O, and O. This way it is been forming a molozonoid. Again, molozonoid bond breaking will take place here. This bond will come onto oxygen. So we will get this diradical where we have C, double bond O. This bond is not broken. We will have this as C with positive charge, O and O minus with R dash. So here this O minus is going to attack here and oxygen is going to attack here. And that's how we'll get ozonoid. These are all the repeated steps. So I'm just rewriting that. So you can see we get O, O here, C here, R dash, O, and a hut here. This is the form which we got. Now without, when it comes to without water, what is happening, correct? In fact, as you can see here, if you leave it for a long time, right, the bond breaking happens such a way that we will get a double bond here, correct? So double bond will be formed here, and this bond is going to break onto this side, right? So because here there is no nascent oxygen that has been released instantly, so we will get this as R, C, double bond O, O, C, double bond O, R dash. So an anhydride form is seen, and this anhydride form, if you treat with water, it will become acids. So RCOOH plus R dash COOH. So there is an experimental evidence of anhydride formation through this mechanism. Got it? But if it was any reducing agent present like zinc or DMS, they will immediately take away this nascent oxygen and end up as aldehydes or ketones. That is a major difference between oxidative and reductive ozonolysis. They turn into cycloalkanes. No, bond breaking is evident. Now, in case if you have, suppose if you have oxidative, let's say you have oxidative here, like this, something it is forming. So in case of oxidative, this is where it, reductive, this is where it will stop. In case of oxidative, this bond will break and it will form OH and OH. Acids will form. No, it may be happening because there is no evidence that has been seen when zinc is being added. That's all. Right? Even if it is happened, maybe that the bond breaking might be happening, but instantly zinc is taking away this so formed anhydrate oxygen, and these two bonds may get terminated. Okay. But in oxidative, there is an evidence of anhydrate, so that's why I'm specifically mentioning it. Okay. Next, see a few examples here. Suppose if you have pH, C triple bond CH, they treat that with O3, second DMS. So this will be pH, C double bond O, C double bond O, and H. And if the same reaction is done with O3 in the presence of H2O, so what do we get, beta? pH, COOH plus HCOOH. Correct? So it will form an acid. Okay. Now, in case if we take any oxidizing agent after this, for example, if we treat further oxidation here, O3, and second case we are writing H2O with some oxidizing agent also, like Tolin's reagent, and so we'll learn about it. So in that case, this would still remain acid, but this will turn into carbon dioxide. Correct? So this has always been a debate, like in ozonolysis, final product is carbon dioxide or formic acid in case of single carbon. If nothing sort of oxidizing agent is mentioned, always end up at formic acid. Correct? If any oxidizing agent is mentioned, oxidizing agent like OA, like, you know, Ag, NH3 twice plus, this is ammonical silver complex, they will convert that into acids. Clear, students? Right. So suppose if at all I give you one example, CH3, C, CH3, H, C triple bond CH, and I treat that with first O3, second H2O in the presence of Ag, NH3 twice plus. And what are the product, students? So it will be CH3, C, CH3H. This will become COOH plus. This will end up at carbon dioxide. DMS is the one which will control the nascent oxygen. Okay. So the single oxygen which is present, what will this do? CH3SCH3. This is DMS, dimethyl sulfur. That it will immediately take away the nascent oxygen and forms CHS double bond O CH3. This is DMSO, dimethyl sulfuryl oxide. Correct? Same is the case with zinc. But H2O is not something which it does. H2O only give hydrolysis, because when H2O has been used, since nascent oxygen is not forming immediately, there is an anhydrate formation which is observed here. Where is it here? Anhydrate formation. It will undergo hydrolysis to give this. Right. Let us see the next reaction type. This is 10th done. At the 11th type of reaction, which is nucleophilic addition reactions. Unlike alkenes, alkynes show nucleophilic addition reactions. So suppose if you have MEO minus K plus in the presence of MEOH. Now suppose if you have CH triple bond CH, MEO minus will act like a strong nucleophile and attacks on this carbon, this pi will shift. Correct? See, the reason for electronucleophilic addition is the carbon having high S character, which means it is highly electronegative, so it would be ready to take electrons. Despite it has an electron cloud around it, when a nucleophile approaches, carbon will accept the nucleophile. So this will get rearranged, the pi get rearranged to form CHOMe with double bond CH minus. That on reaction with MEOH, it will take the proton and form CHOMe double bond CH2. Okay, so this is methyl vinyl ether. Methyl vinyl ether. So it will form methyl vinyl ether. Similarly, if you make the reaction with CH3, C triple bond CH in the presence of MEO minus. So you guys can guess the reaction. CH3, C double bond CH minus with OMe, which again on hydrolysis in the presence of methanol will give CH3, C double bond CH2 with OMe. This is the product form. How this is going to be very useful is because you can polymerize from here. For instance, if I take HCN, right? BaCN twice in the presence of HCN. Right. Now what will be the reaction happening? CH triple bond CH is there. CN minus as a nucleophile can attack here. We will get this as CH, CN, double bond CH minus. Right. So once you get this from HCN, it will pull the proton, it will form CH, CN, double bond CH2 is formed. Now once this get formed, you can see this is called acrylonitrile. This is acrylonitrile. Once you get the acrylonitrile can undergo polymerization. Okay. On polymerization, what would happen? See how the polymerization usually takes place. We have CH double bond, CH2 double bond, CH, CN this way, right? And another molecule, suppose if you have CH double bond, CH, CN this way. Okay. So this pi will attack here, this will move. Correct. So what happens? We will get this as CH2 plus with CH, CN, again CH, we would have this as CH2, correct? Because the minute you add H plus in the presence of acidic medium, let me show it, sorry. First, in the presence of acidic medium, imagine it has CH2 and carbocation is formed here, plus. So this pi will attack on it. So again, we'll get this as CH2 plus CH, CN with CH2, CN, this side and this side it will keep continuing. Again on this carbocation, the third atom will attack. So if you see this way, a polymerization will keep happening. And finally, the product what you will get is CH2, CH, CN, and this will be the polyacrylonitrile, PAN. Industrial name is Orlan. Okay, so basically it is formed this way, AgNO3. When you treat that with ammonium hydroxide, okay, then it will form a complex of AgNH3 twice plus and NO3 minus. So this is called as Tollens reagent. Correct. So what does Tollens reagent do? So we will have RC triple bond CH if there is a terminal alkyne present, and you treat that with AgNH3 twice plus. So when you have this, we will get as RC triple bond C minus Ag plus. A precipitate is formed here. This is actually white color. A white color precipitate is formed. Even if you have H on both the sides, which means both sides it is terminal, with TR, with Tollens reagent, we'll get this as C triple bond C minus Ag plus and Ag plus here. See here, if you see OH minus is already there, no? So there is always OH minus present in the solution, and that is the one which will extract this proton and make it to form it as precipitate. Okay. This reaction otherwise do not go in the forward direction unless there is any precipitate formation is observed. So there will be white color precipitate forming. Now the same reaction, if you treat that with ammonical cuprous chloride, the precipitate is red color. That's all the difference is. That is, if I take RC triple bond CH in the presence of Cu2Cl2 cuprous chloride plus NH4OH. If we use this, then we get RC triple bond C minus and Cu plus. Now this is a red color precipitate, red PPT. Now same reaction if you do it with gold. that is CH in the presence of AuCl3 in the presence of NH3. Same reaction will take place. We'll get this as RC triple bond C minus and Au. This is a yellow precipitate. Next reaction is polymerization. Polymerization reaction. Suppose if I take 3 moles of CH triple bond CH, 3 moles of acetylene, and treat that around 450 to 600 degrees centigrade and heat it, it will convert into benzene. Okay. Or you can treat the same thing with red hot iron or copper tube. Red hot iron or copper tube. So basically, if you take an iron or copper tube and keep it hot at around 400 degrees centigrade and then pass the acetylene gas. Okay, so the vapors that come from here would be of benzene. Okay, so they would become benzene vapors and come out here. So if you see the mechanism, it's like this. Basically, there is a contact of all triple bonds together like this. H, C, triple bond CH here. Then we have H, C, triple bond CH. And then we have H, C, triple bond CH. So this pi is attacking here, this pi is attacking here, this pi is attacking here. So due to that simultaneous attack, benzene is going to form. This is one very, very important reaction. The short form that is used for this is RHFT or RHCT. Red hot copper tube, red hot iron tube. So done with the first reaction, everyone. So acetylene on heating with red hot copper tube, you will get benzene. So in 2003 JE question that was given, prepare benzene from calcium. Okay, so from calcium, we wonder how do we prepare. So if you see from calcium, if you treat that with O2, you'll make it calcium oxide. Then from calcium oxide, if you treat that with coke, we'll get calcium carbide. Correct. So calcium carbide, when you hydrolyze this, we will get H2HC triple bond CH plus CaOH twice. Next, from HC triple bond CH, if you take 3 moles of it in RHCT, so we can get benzene. So you can see that from calcium we prepared benzene. In case if you have CH3C triple bond CH, and that we are treating with RHCT, then here the product that is formed would be same benzene but with 3 methyl groups present on it. What do we call this molecule? Mesitylene. So we get mesitylene formation. Same reaction in case if we take CH triple bond CH, but the reagent I'm changing here, which is nickel CN twice and heat. Then we will get minor product as benzene. This is benzene, and the major product would be cyclooctatetraene. So this is minor product, and this is COT, which is major product. COT is cyclooctatetraene. Right, so done with the polymerization reactions. This was 15th, 16th. No, not needed, beta. It's just a name reaction. Just remember it the way it is.
Can you tell any reason why the 8-member ring is formed?
What, beta?
Is there any reason why the 8-member ring is formed?
8-member ring? Because this is coming due to the complexity of nickel, that's all. Okay. So when it comes to nickel, the way the surface of the metal is, instead of only absorbing 3 molecules at a time, this time it will absorb 4 molecules. Suppose if this is the surface, so 4 molecules of this will interact at a time. Okay. So when they interact with each other, you'll get cyclooctatetraene. Next is dimerization reaction.
Sir, even benzene is more stable, it will become minor product.
Where beta? Here. This depends upon the adsorption on the nickel beta. More molecules are absorbed, then this would come. Okay. Less molecules are absorbed, then benzene will come. Got it?
Yes, sir.
See, next the dimerization reaction. First one. So in case if I take 2 moles of acetylene and treat that with cuprous chloride in the presence of ammonium chloride. Okay, in the presence of ammonium chloride. See, earlier copper and here, see the difference. This was ammonium hydroxide. It was not salt. This is a ammonium hydroxide solution. Here we are taking cuprous chloride in ammonium chloride salt. Okay. So this would give us vinyl acetylene. So which is HC triple bond C connected with CH double bond CH2. So this is vinyl acetylene. So a vinyl group is attached on the acetylene. Correct. Now if you do the same thing in acidic medium, same reaction if you are doing it in acidic medium, CuCl, NH4Cl and HCl. Correct, and HCl here. So first vinyl acetate is going to form, that is HC triple bond C, CH double bond CH2, and then because there is an HCl, again the addition reaction will take place here. So we would get this as CH2 double bond C, Cl, CH double bond CH2. Got it? Now, if you observe, this is called, industrially, this is called chloroprene. The common name used is chloroprene. Chloroprene will undergo polymerization. So if you see, this will undergo polymerization on both the sides where this double bond shifts here. Think this way, this double bond is shifting here and this double bond is moving here. So from one molecule C minus is there, on the other side there is C plus is there. So continuously keep adding that way. So what do we get? The product what we will get here is CH2 C Cl with double bond CH CH2, and that will keep continuing for n moles. So this type of a polymer product is called as neoprene. Neoprene, a very, very important ingredient of synthetic rubber. Okay. So all the automobile rubbers which are been made, correct, tires on which rubber is there, that is all made by neoprene. So this is the mechanism by which it is done. So acetylene is being used with CuCl in the presence of ammonium chloride. So to form first chloroprene. Chloroprene on polymerization will give you neoprene, and this is got to be synthetic rubber. You will come across these reactions again in polymerization. I mean polymers chapter. So start practicing from now itself. What is chloroprene? What is neoprene? Clear, everybody? Let's see how the mechanism works here. So far, I hope all of you understood what is this. Now let's see mechanism. So first we have CH triple bond CH, and we have NH4 plus. So NH4 plus, I'll write it as NH3 H and plus here. So imagine this pi bond is attacking here. Since it will become a unstable, unstable vinyl carbocation, at the same time, imagine another pi bond is attacking here. So what do we get? We will get this as CH2 double bond C CH, which is connected to CH double bond CH plus. This kind of a vinyl carbocation is formed. Okay, and since vinyl carbocation is unstable form, carbon will take away electrons from H, releases out H plus, and makes CH2 double bond CH C triple bond CH. That's why we are using it in acidic medium, so that H plus can act like a catalyst. So it got added first, then it got removed, and we got this structure. Clear, everyone? So this is the first step. See the second step. Once you get this vinyl acetate, CH3C, C triple bond CH, this is vinyl acetate. On this, again, which is more reactive between triple bond and double bond? we know that double bond is more reactive. So in case of NH3 plus here, so it has acidic hydrogen. H plus has been accepted from there. Got it? And as this gets carbocation formation, imagine Cl minus in the solution is attacking here. So we would get this as CH3 with CH, Cl got added with C triple bond CH. Okay. Now this might happen in two steps also. First addition is happened, carbocation is formed, then chlorine is being attacked. Got it? So I'm skipping that step here. So pi is attacking here towards H plus, Cl minus is attacking, you will get this product. Right. So now comes the rearrangement. Once you have this form, see the rearrangement. So we will have CH2H, because this CH3 I'm writing it that way, and we have CH which has chlorine present on it, and then we have C triple bond CH present on it this way. Okay, so this bond will get rearranged to form as a double bond. Chlorine would leave, and chlorine gets attached here with this pi bond attaching H. So a 5-member transition state is formed here. So you can see 1, 2, 3, 4, 5. So this 5-membered cyclic transition state is observed. 5-membered cyclic transition state is observed. From there, it will convert into CH2 double bond CH, C, Cl double bond CH2. This is the final product, which is neoprene. Sorry, chloroprene. Again, I'm telling you students, mechanism is not important. This is not there in the syllabus directly. Mechanism is not asked, but you must know how the working is. Mechanism is just for your convenience. So first one, HC triple bond CH. If you treat with HCl of one equivalent, we know that it will form vinyl chloride, CH2, CHCl. This is vinyl chloride. Okay, so vinyl chloride, if you use for polymerization, what do we get? We will get CH2, CH, Cl, and N times of this. This is polyvinyl chloride, also known as PVC. So all the water pipelines, right, so that are being made are made up of PVC, polyvinyl chloride. Second, HC triple bond CH plus CH3COOH, acetic acid. So in the presence of Hg2 plus, just to make sure we initiate this, just like Kucherow's reaction, so that we can get the product as CH2 double bond CH, and we have OCOCH3. This is vinyl acetate. Vinyl acetate. Got it. So this on polymerization, we will get this as CH2, CH, OAC, and N times. So this gets polymerized to give PVA, polyvinyl acetate. Very important ingredient again in the plastic industry. Next, HC triple bond CH in the presence of 2 moles of Cl2. So this will form CHCl2 here with CHCl2 here. Right. This is known as Westron. Westron, if you use that with alcoholic KOH, elimination will happen here. So we'll get CCl2 double bond CHCl2. Sorry, CHCl. This is called Westrosol. Westron and Westrosol. These two are used as the solvents for dry cleaning. For dry cleaning purpose. Fourth, CH triple bond CH. If we treat with arsenic trichloride, ACl3, we'll get CHCl double bond CH ACl2. So this is known as levisite. The molecule's name is levisite. Levisite will cause blisters. Causes blisters. Next, CH triple bond CH. If you use S2Cl2, dichlorosulfide.
Sir,
Yes, beta.
Sir, in left side, the lower carbon has five bonds, sir.
AlCl2 itself is one molecule, okay, and
Okay, okay.
H is one, okay.
I thought it is to one carbon only.
No. AlCl3 is splitting as AlCl2 plus and Cl minus, okay. I'll explain that also here. AlCl2 plus and Cl minus. Think this way, okay. Addition has happened on it. Next, H2Cl2. Here we would have S getting added on this, and here we have chlorine. So chlorine getting added on both the sides. If you take 2 moles of it, the other side which is there, one side there is chlorine here, this side it will be C minus, so that gets added on to sulfur. Same way here also, C triple bond C, CH double bond C, Cl here with minus, clear, and sulfur got plus already as Cl. So this gets attacked here, Cl minus will leave. So again we'll have Cl, CH double bond CH with sulfur, and this side also will get CH double bond CH with sulfur. Clear on that? And this way if we check out first and then, okay, usually this is done by hydrogenation first. First H2 is done. Let me just show you that first how it is done. H2 in palladium barium sulfate, Lindlar's catalyst, so we'll get it as CH2 double bond CH2. Then S2Cl2 is done. So from there we will get this as CH2 CH minus, and here also we will get this as CH2, and this side we'll get it as CH2 CH2Cl, this way. Correct? 2 moles of it. So if I take 2 moles of it and then react with S2Cl2, we will get this. Correct? So I'll write it in 2 steps here. So first step is Lindlar's catalyst LC, and then S2Cl2. So from here we'll get this molecule. Observe this, this is called mustard gas. When you have 2 moles beta, both sides there is chlorine. One chlorine is removed, it got added on to this side. So we'll get this as C minus, that will attack on sulfur. Again Cl is left, so sulfur will still have positive charge, and again another mole of CH, that Cl minus got added onto the second mole, minus has left here, that has attacked here. Okay.
Yes, sir.
None of these are important in terms of mechanism. These are all just miscellaneous reactions. You just need to know the structures. What is a mustard gas? What is lewisite? What is Westron? We just have to practice that one. Next, if I take 2 moles of CH3 triple bond C and heat it with sulfur, we'll get thiophene. S and S double bond double bond. Just like if you take 3 moles and heat, we got benzene. In sulfur, if you do it, we'll get it as thiophene. Reaction with NBS, N-bromosuccinamide. So in case if we have CH triple bond C, CH3, when you have a double bond and the next carbon which is sp3, what do we call it? We used to call it as allyl. If it is triple bond, the next carbon is called propargyl. This is propargyl, ARGYL. Okay. So in reaction with NBS, we will get this substituted as CH2Br. Again, radical substitution with NBS, you know that.